This international research activity on ventilative cooling is one of the reasons we have this seminar today, because tomorrow and Friday we will have a workshop where we will discuss the research progress in this project. In the presentation, I will give first a short introduction to the background. Why did we start this research activity? Then, of course, I will say something about what I'm doing myself, because this is what you think is most important. And then in the end, I will say something about the annex and the organization of the work. So I just need to find out which one is the... Yes, perfect. The background for the project. If you look at the development in the building sector, we in all countries have a need for increased or improved energy efficiency in our building stock. This means that we construct new buildings, we renovate old buildings, so their energy use is much lower than before. This has an impact on the conditions in the rooms. We focus a lot on decreasing the heating need in our buildings, because this is the dominating energy use in our buildings. And what happens when we optimize the heating need is that there is a side effect that we sometimes increase the cooling demand, or if we don't have any cooling, then we might increase the temperature levels in these buildings. And if we look at some of the, you could say, recent demonstration buildings which are, you could say, fulfilling our future goals for energy efficiency in buildings, we can see that elevated temperature levels is one of the bigger problems in these buildings. And actually, it also shows that it's not only in the summer period where we are used to focus on cooling problems or overheating. It's actually more or less the whole year round. Even in the winter time, in the heating season, we might experience issues with overheating if the design of the building is not appropriate, or if the control of the systems does not work or are not used appropriately. One of the reasons that we might experience problems now that we have not seen before is also due to the difference in technologies we apply. So far, we have came a long way of improving energy efficiency by improving insulation, by improving air tightness, by improving heat recovery. These are all what I would call robust technologies, which does not have any influence of the use of the building or have any interaction with the users. But if we look at the technologies we are applying today to further improve the energy efficiency, it's technologies like demand-controlled ventilation, solar shading, daylighting control, lighting control, window opening. These are all technologies that has a large degree of interaction with the users, and where users influence a lot the performance of these systems. So this means that the building performance becomes much more sensitive to control, and it becomes much more sensitive to the different degrees of user interaction. And this also means that a proper design might not function acceptable in reality, because it is very dependent on if these technologies are used appropriately. If we look at offices, we could say that we typically always, or at least in the majority of offices, have a cooling need during occupied hours. And so this means that cooling in offices is not a new technology, but there is an increasing need for cooling. If you look at the free cooling potential, this has been widely used in mechanical ventilation systems. I'll come a little back to how we can improve this, because still if we use the free cooling potential, we might still have a large energy use for transportation of air in the building. But if you look in offices, then you could say natural and hybrid ventilation systems are still limited in many countries for ventilative cooling purposes. I will give you an example of some of the work we are doing ourselves to look into how can we improve the free cooling potential of the outdoor air for cooling in offices in a cold climate. And this is an example of a relatively new office building in Denmark. And if you look at what is necessary to cool down this building, then you could say typically we supply air. We cannot supply air with the outdoor temperature, because if we do that, there will be too high draft risk in the occupied zone. So this means that we need to apply heat recovery or to preheat the air, so we have a supply maybe at 18, 19 degrees. This means that we actually need to have you could say an airflow on an air change rate of in this case about 3.5 to 4 air changes per hour. So this means we need to transport a lot of air in order to cool down the building. If we could use the outdoor air directly at the outdoor temperature we have in the winter time, this air change rate could be reduced from 4 to something between 0.5 and 1 air change per hour. So this means this would drastically reduce the energy use for transport of air in the building if we could use the outdoor air directly. Therefore, we have been looking into seeing if we could use what we call diffuse ceiling air distribution in the offices instead of the normal inlet openings. And of course, we know about diffuse ceiling inlets from clean rooms where we have a high air velocity in order to what's called to have a kind of piston flow in the space. And there the air distribution is mainly driven by momentum. But if we look at offices, we could say, well, the airflows we have in offices are, of course, not 50 or 100 air changes per hour like it is in a clean room. It's much lower, and actually we want to go maybe to only 0.5 or 1 or 2 air changes per hour. So this means that the air distribution in these spaces will not be controlled by the inlet, but it will be controlled by the airflow from the buoyancy sources, heat sources that are in the space. So we have been looking into different types of diffuse ceilings. You could say it could be one type which is a fully diffuse, where the ceiling, the ceiling panels are diffused for air. It could also be that the air actually is coming in the fitting system for the ceiling. So the ceiling is tight, but there are gaps between the different panels for airflow, or it can be a combination. And actually we have tried to compare the performance of such a system with the performance of different types of ventilation systems in rooms. And the way we compare these systems is that we use such a design chart like this one, where we have the temperature difference between supply and room temperature, and we have the airflow rates out here. So this means that we will have you could say a certain of, depending on the cooling need, we will have a certain curve for a certain cooling need, which gives the relation between temperature difference and flow rate that gives the cooling need we have. Then you can say there is a minimum airflow rate we need to have in order to ensure air quality. There's maybe a too high airflow rate will create draft, and maybe if you have too big temperature differences, we will also have draft or too high temperature gradients in the space, and that could also be a maximum capacity of the system. So this means that we will be left with an area where we could say this is the area where the system can work due to constraints of the system and due to draft risk or anything. Yeah, also noise level, I forgot that. And this is a curve. It looks a little bit, maybe a little bit messy, but what you can see here we have the minimum airflow we need in order to ensure indoor air quality. Then we have a curve like this, which is for these radial ceiling diffuser. So this means that any combination of flow rate and temperature in this part here is comfortable, and we don't have problem with the draft. If the temperature difference becomes too high, we get problems with draft, or if the flow rate gets too high, we get problems with draft. So this is the area that works. There is another curve here, which is the the sidewall mixing ventilation supply, which have a much more limited application area without creating draft. And then this one up here is the diffuse ceiling inlet, and you can see that you can actually provide quite high cooling rates, or it has a quite high cooling capacity, and these are the limits of what we could do in the experiment. So we didn't test for temperatures with temperature differences higher than 16 degrees, and this was the maximum flow rate we tested it with. So we actually have not seen what are the borders. Now we are doing experiments to temperature differences up to 30 degrees to see if it still will work proper or provide comfort even if the temperature difference is 30 degrees. And that is necessary if we have to have it to work in Denmark, even in the cold winter periods. So these are some of the issues we are looking at. So this is not, you could say, focusing on the summer situation, but actually focusing on the winter situation and optimize the use of free cooling potential in winter. In the project, we have defined what we call the kind of definition of how we see ventilated cooling. And we have defined ventilated cooling as application of ventilation airflow to reduce cooling loads in buildings. And we limit ourselves to look at ventilative cooling that uses the cooling and thermal perception potential of outdoor air. So this means we don't look into the different technologies you can use to decrease the outdoor air temperature. It could be evaporative cooling, it could be ground cooling or whatever. We are not looking at that. We are looking at using the outdoor air as it is and see what is the potential to do that. And then we are looking into into different driving forces. Some are looking mainly into using natural driving forces to drive the air. Others are looking into mechanical systems, and also some are looking into different combinations of natural and mechanical systems to drive the air. Ventilative cooling, we think ventilative cooling has you could say, a large potential for cooling in buildings. Both because it's already there. We have systems, we have ventilation systems, we have windows and the possibility to open those to improve natural airflow through the building. We have in many European countries an outdoor climate where the outdoor temperature is lower than the temperature we want inside our buildings for long periods of the year. And we can, by ventilative cooling, especially when we use natural systems, provide very high airflow rates and thereby also a relatively high cooling potential or cooling capacity in a large part of the year. And especially if we look at the progress in building energy efficiency, where cooling not only is an issue in the peak summer period, but actually is an issue in a large part of the year, of course the cooling potential of the outdoor air increases also. If you look at the application of ventilative cooling, we could say that on one hand, ventilative cooling is not applied very much in residential buildings. I think the main reason for that is that it has not been an issue so far. Cooling has been limited to, you could say, peak periods during summertime where it's very warm outside, and not been an issue you need to address in longer periods during the year. So therefore, we don't have, you could say openable windows are the solutions we have in buildings. And we have not, you could say, more sophisticated or more intelligent solutions than manually openable windows. And occupants often have difficulty in finding out when to use these windows and when not to use the windows. While if you look in offices, I think it's a standard solution to, especially in offices, to use ventilative cooling, both in mechanical systems, which of course has the limited benefit because we have a fan energy use for when you use free cooling, and if we require large flow rates to cool the building, the fan energy use increases quite rapidly. So this means that or you could say, there are some limitations in using mechanical ventilation for ventilative cooling due to the system capacity and energy use, while ventilative cooling by natural and hybrid ventilation is known in many cases, but I think it's only used efficiently in a few cases. Maybe not in Britain or here in UK, because you are using much more natural ventilation in the UK than we see in many other countries. So you are probably the exception from the rule. So what about the annex? The objectives of the annex, we have 4 objectives of the annex. One is to, you could say, improve and evaluate methodologies and tools to predict cooling need and overheating in buildings. We see that in many countries, the prediction of cooling need and overheating is not a standard, as you could say, methodology to use, especially when you design residences. This is not something you do automatically. It also means that there are not, you could say, very many easy to use or quick to use methodologies to estimate the performance, the cooling, the overheating risk and cooling performance of buildings. So we need to improve that if it should be, you could say, integrated in the normal design procedures for residences. For offices, you typically use more sophisticated tools to check the indoor environment. So there you often take it into account in the design. Then we also are looking into energy performance calculation methods, because typically energy, or we can see from our review that in many countries cooling and overheating is not part of the calculation of the energy performance of buildings. So this means that this is of course contributing to increasing the risk of overheating and increasing the risk of a cooling need if it's not taken appropriately into account in the energy performance verification method. So there we will be looking into methodologies to integrate ventilative cooling, overheating into these methodologies. Then we are also looking at the solutions, both looking at how can we improve the existing ventilation solutions in buildings to give a better performance related to cooling, but also look into new solutions that can create comfortable conditions in buildings on cooling. And then there will be a number of case studies that will be monitored and evaluated to demonstrate the performance of ventilative cooling. This was the objectives. Then the outcome, what comes out of it. We will provide guidelines for ventilative cooling and for reducing the risk of overheating by ventilative cooling in buildings. We will come up with some recommendations how cooling and overheating risk can be better integrated in our you could say legislations and in our energy performance calculation and verification methods. So it's naturally to take cooling and overheating risk into account, as well as heating and other energy uses. And then there will be developed some new solutions for ventilative cooling in the annex, and we will have these case studies to document the performance of different systems. The work is divided into you could say 3 work packages or 3 subtasks, as we call it in the IEA terminology. One is looking at the methodologies and tools. So these are the design design methods and tools, energy performance calculation methods and tools are looking into that. Subtask B is mainly looking into the technical solutions, both improving existing and development of new solutions. And then subtask C is looking into the monitoring and evaluation of case studies. So it's a very straightforward and typical division of the work. This is, here you can see the participating countries. We have 6, 9, 12, 13 countries, mainly of course there are many European countries, but we also have representatives from China, Japan, and the US. And here you see the persons. I'm the operating agent or the project leader of the whole project. And then we have leaders of the different subtasks from the different countries involved. So here you can see who to contact if you want specific information on specific parts of the work. Yes, thank you for your attention. Information about the annex you can find on this website here. We have a common website with this European initiative on ventilative cooling, Venticool. So here you can see both something about the organization and also something about the annex.